everyone. Can you all hear?
I'm here.
Okay. Okay, well, it's just a couple minutes after 1 here, so we're going to go ahead and get it started. Let me just introduce the presentation for you. First off, if I could have you all please take a look at your microphones and please mute them so that the background noise doesn't come over top of us. Today's webinar is for TC or TRT testing for geothermal systems. It's sponsored by the Ground Loop Design Software and Precision Geothermal groups. It's the fourth in our series of monthly presentations for geothermal design professionals. If you want to review this one or any of the other presentations that you might have missed, you can visit the Ground Loop Design website and just click on webinars, and we've posted them there. It generally takes us a few days after the webinar to get it posted. They run about 40 minutes each, and we'd encourage everyone to take a look at these, and if you have the opportunity to ever participate in training such as the CGD program through IGSPA, or training for other design tools such as Trace, GLD, HAP, and others, we encourage you to do that. Today's presenter is David Henrik. David's the Vice President of Precision Geothermal, who manufactures the GeoCube. He's a mechanical designer, professional driller by training, and has been involved with our industry for about 20 years. He's NGWA certified driller, an accredited installer through IGSPA, accredited trainer, and areas of specialty include the closed geothermal design and construction, geothermal monitoring, acquisition, and he's the lead mechanical designer for the GeoCube, which is an industry-leading thermal loop testing system. David's a member of ASHRAE, Canadian Geo-Exchange Coalition, and he currently is serving on the board of directors for NGWA. And this presentation will be about a half an hour with Q&A at the end. So with that, I'm going to turn it over to David.
Good afternoon, everybody. My name is David Henrik, as Jeff introduced me. We're going to run through some basics on thermal conductivity testing. I'm going to try to kind of breeze through it and then let you guys do some Q&A at the end. That way I can make sure we answer any questions that anyone may have individually. I'm going to try to spend a little bit of time, particularly on when you order a TC test, because there's always a little bit of confusion about when do we get the TC test working in a project. And sometimes, it's just like, oh, we're going to do geo, so let's do a thermal conductivity test. Well, there's some other steps we can do to actually kind of scientifically analyze when we order a test, and we'll cover that today, as well as looking at some data from some good and bad tests, what the data acquisition means, how the tests run. So without any further ado, we're going to run right through this. Now, I don't know if Jeff mentioned or not, we're going to record today's presentation, so please, if you ever need to reference it, Jeff will get that up online for everybody. I noticed that Tom has his hand raised right now. I'm not sure if that's inadvertent or not. Tom, do you have a question? Okay. I guess I'm going to start rolling through the presentation. I'm going to switch over to the slideshow real quick. All right, so we should, Jeff, can you confirm for me? I got two screens in here. I haven't run this new PowerPoint software yet on this. Are you seeing the proper screen, Jeff?
Yep.
Okay.
Good to go.
Great. All right, so today we're going to cover just some basics on the line source theory, just to help you kind of understand how we bend the theory to fit our application, because there are some differences between the line source theory as it's written and the actual reality of what a thermal loop is. From there, we're going to cover kind of the basics about the test procedure, how it works, look at some report and some data. The data analysis act, we're going to cover that down the points of interest. So if we're running over time, we're going to chop that end off. Looking at the impact of a design really kind of highlights why you need to do a design, or why you need to do a conductivity test, because the impact on the design can sway it so much depending on the size of the system. And then the design process when we go to the TC test. Okay, so the line source model. The mathematical model for the line source theory assumes that you have an infinitely straight, infinitely long line with the thermal radiation pattern. So that's kind of the theory. That's what the math is assuming you have. In reality, a thermal borehole, a geothermal bore, looks something like this. It's not infinitely thin. It's not infinitely long. It doesn't have a single heat source. So there's some things that we need to do to manipulate the math to make it work, and some other things we do during the test that turn what you see on the left, the actual bore, into what you call the skin model, where basically we thermally saturate the entirety of the bore, making it homogeneous, and then just having a thin resistance layer. So we're taking, in reality, the physical makeup of the bore, and when we insert heat, we're actually going here. We're actually turning into something that will fit that line source model. What we're doing to get that skin model, you see this part of the graph where we have our greatest increase in temperature during the test. That's when we're thermally saturating the borehole to make it look like that infinitely thin line, that homogeneous line source. So what we're doing is just saturating the borehole with heat to the point where basically, if you took a colander and you started filling it with water, well, some water would run through the colander. And as you kept on pouring more and more and more water, faster and faster and faster, eventually you'd overfill the colander. Well, what we're trying to do is basically get to that point where we've saturated that colander so you have one homogeneous flow running through, heat flow running through the entire bore. And so that's what we see when we add heat in this breakdown period, which usually occurs in the first 10 to 12 hours of the thermal conductivity test before we get to more of the steady state condition here towards the end. We're trying to make that bore go from this to this. And that is kind of how we bend reality of a bore, which has a three-dimensional makeup, into something that's much more linear, much less dimension, or much more dimensionless. Okay, so your typical thermal conductivity setup: GeoCube on the right, generator on the left. People ask me all the time, well, how much energy do you really need to run a test? The truth is, most units are running anywhere between 5 and 10,000 watts. Now, in order to achieve the recommended power stability, you're going to have to use a generator that may be as big as twice the size as the wattage that you need to make sure that you're getting good, steady power. I always recommend that when the conductivity test is ran, that you use diesel-powered generators. Gas-powered generators have a tendency to really vary depending on what the outside air conditions are. I mean, at nighttime, they run very well when they stay nice and cool. Then during the daytime, when it gets hot, they have a tendency to have a lot more power fluctuation. Diesel generators have a tendency to keep the power variation less than 1.5% and stay real consistent, considering the runtime. I mean, when people run generators, they're not necessarily counting on running them for 40-plus hours straight. So we found the best power consistency comes from diesel power generation. That right there is a 30 kW unit and gives us consistent power every time. That's really the reason we run something that big and recommend running something that big, just the consistency. Okay, so basically when you go to do a thermal conductivity test, the things that you're after at the end of the test are what's the native ground temperature and what's the thermal conductivity of the soil. Those are really the only two things we'll be measuring during the entire test. among this, so I guess you have a fringe borehole thermal resistance calculation to back out at the end. But the two physical qualities that you really have to like: ground temperature, thermal conductivity. So the first thing you do when you get to a site is you're going to want to take a reading of the ground temperature, because once you start your test, you're going to disturb the native ground temp and not be able to measure it again for several days. So testing the ground temperature is the first thing you do. You can either do it with the equipment. Some people actually will have a probe that they'll lower down inside the loop and take temperature at different footage intervals and then average out the temperature for the entire loop. Most people that I've seen recently doing the tests have been just using the log temperatures, the early data that comes back on the data logger. So you'll set up the equipment, start up the circulating pump, and then just let the water circulate for 20 minutes or so you get 5 to 10 good readings. Most loggers are taking 2-minute sampling intervals, and that allows you to get enough data so you can see about what the ground temperature is, because eventually the pump adds a little bit of heat to the water, so eventually you're going to start disturbing the ground temperature just by circulating the solution through the test equipment. After the test equipment has been hooked up and you have purged all the air from the loop, air purging, very important. Any kind of air that would be left in a loop could conceivably actually get into the pump, cause it to airlock, cause the fluid to freeze up, and then you end up with a flash boil of the water when you mix the heating elements. So being careful to purge the air, very important, because it can also cause a lot of low flow conditions, which will vary the heating state and flow state in the test throughout the 40 plus hours that you're running it. Running the test, simply got the fluid circulating, and then you just inject, turn on enough heating elements to meet your 15 to 25 watts per foot as recommended by ASHRAE. We usually just try to shoot for that 20 watts per foot mark, and adjusting the voltage on the generator, adjusting the number of heating elements to make sure you meet that energy input level. Very important. I always try to shoot right down the middle. That way, if the power were to vary a little bit during the test, at least your heat input rate has a better chance of staying in the range. And with the GeoCube, it actually makes data analysis gets very simple. We literally, about 5 minutes after you complete a test and you get the data logger out of the GeoCube, you can have it hooked up to your computer, downloading data, exporting it to GLD, and running your test. Literally 15 minutes after the test is completed, you can have some preliminary results that you can share with someone. It's one of the huge advantages that GeoCube has over a lot of the other equipment on the market, because you don't have to send your data away for analysis. The GLD software actually analyzes power quality, temperature deviation, as well as late fit temperature data to make sure that you have a good slope stability for when you analyze the thermal conductivity. The thermal conductivity is directly related to the slope of the line of the natural log graph of the delta T over time. So analyze the data, get the reports, submit the reports, project completed. I always find it interesting when I see thermal conductivity test reports that are half a ream of paper thick, because really, at the end of the day, there's really only 3 key pieces of design data that are coming out of the thermal conductivity report: the thermal conductivity, an estimation of the thermal diffusivity, and the ground temperature. Those are the 3 key pieces of design information that are coming out of the test. When I see some of these 20, 30, 40-page reports that I've seen, it's kind of like, what could you possibly need that much paper to submit 3 pieces of data? Really, you just need to kind of see the graphs, make sure that the temperature data is nice and consistent, make sure the power input's consistent, and everything else is pretty much is what it is. Here's some of the ground temperature measurement scenarios. as I said, the most prevalent method I've seen recently is the actual just circulating solution through the unit. Test equipment, the GeoCube is what we, of course, manufacture. It's a very durable piece of equipment, really designed with a couple of key factors in mind. One is safety. Number two is durability. Ease of use is pretty unparalleled. It's a pretty easy plug-and-play device. A little bit of setup, a little bit of time gets involved in running your data at the end, but it's kind of one of those, once you learn it, you know it, and it becomes second nature, and it's very easy. We have several people in our office here that we've taught to do thermal conductivity testing, and usually after one or two tests, they've got the procedure down real well and don't have very many questions after they've done it a couple of times. So we're pretty proud of how easy and safe the equipment is to use. Some of the tools of the trade that you take out, you're going to have, when you're doing conductivity testing, you do have some work that has to go on, getting the loop hooked up, getting the air purged out. That's crossover valves for making sure you get all the air removed towards the top of the screen. Just a quick look at what's in the toolbox, and really it all fits in a nice box. So it's not, you can't go out completely unprepared, but at the same time, it's not like you need to bring an entire service truck in order to make sure you're equipped to do a test. Kind of a cutaway of what the equipment actually is doing, what's actually inside the box. There's really not a terrible amount going on inside one of these conductivity units, and this pretty much goes for everything you'll see in the U.S. So in Europe, they've got a few other pieces of equipment that they'll run heat extraction as well as heat injection, and they've got some other theories that they've worked on over there. But all the studies that I've read up and all the dissertations that I've read over the last several years show very, very marginal increase in accuracy over the heat injection method. It's generally less than like 1 or 2% difference between like a delta T method versus where they're actually keeping a constant delta T on the heat injection. What we're doing in the U.S., and this goes for probably 90% of the tests that happen in the U.S., we're just doing a constant heat flux, which means we have a constant rate of heat we're adding to the loop. There's some other methods out there, including a constant delta T, and that method insulates you a little bit from atmospheric effects because your pump can automatically speed up or slow down to maintain that delta T, but the accuracy is pretty marginal, and the equipment gets a lot more sophisticated and a little more expensive. So the constant heat flux seems to be a constant, or the more prevalent method used in the U.S. Inside the unit, simply, there's your heat rate, your heating elements. There's a number of heating elements that will be on, keeping a constant heat rate being pushed through the system by a circulating pump. In the line, we'll capture the supply temperature and the return temperature as it's flowing down the loop. The GeoCube also monitors the flow rate. And the flow rate's really not used in any part of the calculations. It's more just the validation of that there was a consistent state throughout the test. You want to see your flow rate be within a half a gallon a minute or a gallon a minute throughout the entire test. And that monitoring that allows you to validate that. As I was saying, the reason why we recommend large diesel power generators, because power is everything. As long as you've got consistent power input throughout the entirety of the test, you're going to get very nice, clean temperature curves throughout the test, where you're going to have data that's in a nice, gradual line. And when you get out to your analysis period, which is out here in the the 12 to 40-hour period, you're going to have an actual line that very closely resembles the line of best fit. Because GLD actually will go in, look at your data, and will program in a line of best fit for you. And you can look at this line where your thermal conductivity is being calculated from, compared with your data, actual raw data that you collected, and see if they fit real well. We also do a more sophisticated analysis on your results page that shows you what percent you were within actual to calculated, but visually is one of the best ways to inspect it with the human eyes. Kind of a closer look. But this is a zoom in on a very specific time period of the line of best fit in that natural log graph. Just kind of showing you where the line of best fit is versus the actual data. You'll see that there is a little bit of variation that'll happen over the test, whether it be atmospheric effects, but what we're looking at here is very minute changes over time, and it really allows you to kind of zoom in real close and see if your line that the calculation's being done on fit the data analysis. Fit the, pardon me, the calculate, or fit the line of best fit that GLD programs in for you. Then, as I was saying, in the results page, you actually have some thresholds that you can program in. ASHRAE has set up standards for power deviation, power variation. Then we've got 4 other categories that we felt were important that nobody's really kind of laid down the law on yet. In here, there's a threshold for the stability of temperature to make sure that your temperature variation was minimal throughout your entire test, as well as the consistency of the flow rate. The slope stability, that is the line of best fit that gets programmed into that natural log graph of time, and you want to make sure that there's not a lot of variation on that slope line to the actual collected data. But typically what we see when we analyze data is you'll see a slope stability of anywhere from 15 to 30%. So it's not like the other ones that you're expecting 1 or 1.5%. There's a little bit of fluctuation, as I showed you on the other graph. It's very clear that there's a little variation, and you're not going to get away from that just because of atmospheric effects and the fact that there is a little bit of deviation in the power supply as well. And that gets it really kind of multiplies itself when you're looking at things as touchy as just a straight slope line. Of course, the data we're looking for out of here, we have thermal conductivity, which we calculate an average heat flux throughout the test. The borehole thermal resistance kind of gives you a clue. More than anything, this value here allows you to look and make sure that the borehole that was installed was the borehole that you specified. Because this will, you can't really, the BTR is nice to know, but it's pretty tough to take one borehole out of a couple hundred and assume that borehole thermal resistance is going to be the same for all 1 to 200 boreholes. The borehole thermal resistance is it's a number that's extremely easy to manipulate and change because it's based on pipe placement in the borehole, the quality of the grout, if there's a water vein that goes through it. There's a lot of different variables that go into borehole thermal resistance. So you'll normally see when you get a borehole thermal resistance value from a conductivity test, it'll always be slightly lower. I guess from what I've seen, my experience, I've always seen that the reported borehole thermal resistance on the test is slightly lower than what GLD will model from a theoretical basis. But I usually caution people on, unless you've done a pretty good sample of the bores and actually can establish a representative average borehole thermal resistance, shy away from using too aggressive of a borehole thermal resistance value because you wouldn't want to ever overestimate how much energy you can move through your leach field. And as I said, the thermal diffusivity is more of an approximation based on tabled data. You can do calculated thermal diffusivity based on specific heats, densities, and the like. But again, that information sometimes is hard to quantify in a borehole. It really only applies to bedrock formations. Drift, sands, tills, clays are much harder to classify than bedrocks when it comes to calculated diffusivity. So a lot of times you'll end up with somewhere in that thermal diffusivity, whether it be calculated or estimated, there's going to be some estimation at some point, because you'll have a very difficult time physically qualifying all the data that needs to go into a diffusivity calculation. Then the reports. Our reports are something in the order of 8 pages long, and they used to be shorter, but people didn't feel that we were putting enough paper on their desk. So we put a couple extra pages in that showed or explained some of the thresholds, some of the ASHRAE recommendations, what's going on with the test, just some kind of canned language at the end of them explaining what a test is and what it does. And at the end, though, if you're a designer, the information you're looking for is right here in this box. So calculation results, conductivity, diffusivity, and then down here, the ground temperature. Nice, concise report. Everything you'd expect from GLD. Okay, so impact on designs. We're going to take 2 different scenarios here. On the left, we've got one scenario when we estimated that the system would have a conductivity. In our preliminary design, we estimated the conductivity would have a 1.42, and the soil would have a conductivity of 1.42 and a diffusivity 1.26. After running a thermal conductivity test, we found out that it calculated conductivity of 1.89, and an estimated diffusivity was close to 1.3. So taking into account that information, we have scenario 1 had about 47,000 feet of borehole length. Scenario 2 has 41,000 feet of borehole length. So there's a reduction of nearly 6,000 feet of bore running that conductivity test, which gives you a pretty solid financial justification. Well, why do we need a test? Why don't we just estimate, look at some local geologic data and try to just figure out what it would be? Well, running a test can get you accurate data on the site and really allow you not only to design the best system based on the best science, but also allow you to potentially accurately lower your borehole lengths to where you'd have a real solid justification to run it. Okay, so when would you order a TC test? Do we do it right away when we know we're going to have a geothermal system going in the project? At what point do we want to get the data? Because you really don't want to get a test right away, because you want to get through some kind of preliminary design where you can establish steps and things like that. But that also requires you to know about how many borings and other information about the test. So as I see it, as our group in here sees it, you want to pretty much go through your basic feasibility study. You want to go through and get your energy loads done. When you have a solid set of energy loads, do a preliminary loop design. After you've done that preliminary loop design, you have your energy loads, you can go through and do a more intensive feasibility study based on those preliminary figures that you had come up with, and figure out, is geo a good fit for the project? Because quite honestly, not every project is going to be a geothermal project. I mean, I would love it if they were, but sometimes it just doesn't make sense. Sometimes you've got a cooling load that's just so out of hand that your heat exchanger would be unaffordable. There's a point where geo makes sense and geo doesn't. So if you would have said, well, we're looking at geo, let's do a thermal conductivity test, and let's do it as part of the basic feasibility study, and you get down here and find out that you've got a $5 million loop field, well, that was just a waste of investment. That bore now needs to get sealed up and needs to go away. So wait until you've got a good go-ahead on the project, when we know everything's going to work out. Apply the financial case for the TC test, find out if you can do one, and then order one at that point. And then based on that information, you can optimize and specify. So, you have basic feasibility, some information there. I'll have Jeff email out this presentation so everyone can kind of thumb through this stuff a little closer if they want. But basics, rule of thumbs, look at local geology, use GLD, do a basic financial model. The tools are all in there. It takes you minutes to do. Basic feasibility study looks like this. Gives you some energy costs, annual energy costs, gives you some life cycle energy costs, gives you some numbers you can present to an owner and say, well, this is what we think it's going to cost you over this amount of years. They can compare it to baseline, see if it looks good. From there, say, okay, let's do it. So you get into your preliminary loop design. Here's where you start establishing the number of bores, the depth, because you need to specify how deep you need your how deep the bore you need for your thermal conductivity test. Because if you had let's say here we think we're going to need 200-foot bores, we start running our preliminary design and realize we need 300-foot bores. Well, a test from a 200-foot bore has nothing to do with a 300-foot bore. The geology can change, temperature can change, moisture content can change. It skews everything. So you need to make sure it's important that you identify about how deep the bores are going to need to be. So you better have some idea of how big the field is, how much space you have, and how deep you're going to need to go. Optimize your financial model after you've done your energy loads, give yourself some comparative data, look at your life cycle cost totals and your annual energy costs. See if there's a financial justification for the loop field. Everything looks good. Everything looks good at that point. You'd look at, well, do we need a TC test? And the answer is you perform the thermal conductivity test if the cost of the TC test is less than the cost difference between the best case and worst case design scenarios. For example, if you're drilling the footage that we saw before, approximately 47,000 feet, if the soil conductivity is 1.42. If the soil conductivity is 1.89, we're going 41,000 feet. Cost difference between best case, worst case scenario, or pardon me, the footage difference, approximately 6,000. If the drilling costs are approximately $12 a foot, which I think in most areas are at least that, the total cost difference between scenario 1 and scenario 2 is $71,000. There, you have the cost of a TC test is generally less than about $10,000. It's an easy cost justification. The thermal conductivity test could save you up to $70,000 between the best case and worst case scenarios. So run the test. Sometimes it'll save you. Sometimes it'll save you money. A lot of times it'll save you money on the end cost of the field. Every time it'll at least give you some solid data that you can design, scientifically design a system instead of trying to estimate based off of neighboring geologic logs. From there, you can plug in actual data, optimize your loop design, do a financial model, and there you go. Okay, we'll cover a few points of interest here. The first thing we're going to look at is the data analysis and spotting bad data. At Precision Geothermal, we spend quite a bit of time looking at people's data and trying to figure out what happened, what went wrong. Can we use this data? What parts can we use and what parts can't? Because these data points that you see on this front page, you can see this power. And these are graphs that all come out of the GLD software. They're all part of the reports package in GLD. And you can see consistent power. You can see how consistent these temperature curves are and how well the lines of best fit in with the actual data. Flow rate was within a half a gallon per minute through the entire test. This is good data. This is what good data looks like when you see it graphed out. Question here, as you look at this graph, is that usable information or just data? Looking at some of the other graphs, you can see that your power fluctuation was pretty drastic for the entire test, which of course, is going to skew your results. When you have unstable power, and this is what power, I've seen a lot of gas generators put out a power line that looks like this. It's just a messy, squiggly, inconsistent power drop through the entire test kind of scenario. And what it does to your line is it just hits, and you can see where you have a dip in power, then you have a dip in feed, a spike. You see that kind of label steady off as it went up, then went down to the flat spot. You can see it through the entire test, how it just kind of, the power line pushes your temperature along the entire test. A closer look in on that. That's pretty unsteady heat rate. More data. I talked about what air purging can do to your system. That's what happens if you leave a little bit of it. Pardon me. I just muted John for us here. All right, so this is what happens if you don't purge your air. So you'll ramp up, you'll get some decent flow, and you'll see a little fall off, and then it'll just kind of sit there. And then over the course of the test, usually that air bubble will come free at some point and spike you back up and really alter your flow. And what happens to your data is you end up with that lull, and then you have that burst of flow, and you're getting a lot of heat pushed into the ground, and then you have the fall off again. So the nice thing about GLD is that it graphs all four of these characteristics of the data, and you can look at everything side by side and identify if everything's steady state or not. Some other interesting things to look at, and this is some research that was done by Oklahoma State University, I believe, where they kind of did some power interrupted tests. And it was interesting. So they ran the test on the bore. And this goes to, because people experience power drops throughout their test. The question is, how much power loss is too much power loss? If you have a generator shut down for 5 minutes, are you fine? 10 minutes, are you fine? 2 hours? At what point is it too long to continue a test? What you can see here from this data, though, is that the uninterrupted test runs along these squared dots. The interrupted test, we have this dropout here, it's about 2 hours, shows that it recovers and goes here. So conceivably, you can see that that line pretty much rebuilds itself even after losing power for 2 hours. So people ask, well, how much time can you go? Well, it lets you know that any power loss less than an hour probably will allow you to get your data curve rebuilt, and you'll be able to probably truncate the bad information in the middle of the test and still get usable data. Kind of interesting take. And then the other question people ask, well, how long do we need to run a thermal conductivity test? The nice thing about the GLD software is you can alter the amount of time that you need, that you're going to run your test for. So you can truncate and run your test from 12 to 20, 21, 22, 23, up to 40 hours. What I have people look at is, at what point does the data start flattening out? The thermal conductivity here, you can see it's still building and building and building. At some point, it's going to hit steady state results. And with GLD, you can run this. You could run a 50-hour test and test it in 30, 31, 32, 33, and figure out how long of a test you need to run. And typically, you'll be able to figure out for an area how long you need to run a test. With higher TC formations and lower TC formations, will hit steady state periods at different times. Another thing we run into a lot is groundwater flow. If you have groundwater flow, you'll have your temperature graph will end up looking like this. It'll just hit a plateau at the top. Instead of having that nice gradual curve that kept on climbing, the water will just carry all the energy away and the delta field just stop. And so it'll just hit a point where it'll just literally plateau. And that's a really good indication that there's some groundwater movement going on in your bore. And what that'll do is that'll skew your thermal conductivity value to be way off the charts. And that's how you spot it. Last slide. People ask borehole spacing and borehole spacers, do they make a difference? Here's some more data from Oklahoma State University that shows what happens to the borehole thermal resistance values and what the conductivity tests look like with and without spacers. When you have pipe spacers on, you can actually see that the delta T and temperature feed stay lower over time the whole without spacers. Basically what they do is they just decrease the borehole thermal resistance, allowing you to transmit more energy into the formation. So thermal conductivity testing, not only is it good for practical design purposes, it's also fantastic for research purposes and validating is a borehole working the way it's supposed to work? What makes a borehole work better than other things? They're great research tools, and there's a lot of information you can glean out of a thermal conductivity test when your eye gets kind of adjusted to looking for what's there. Ran about 10-15 minutes over. Apologize for that. It's a lot of information to try to cram in a short amount of time, but I would be happy to take some questions here for a little bit if anyone has some. Feel free to unmute your line and we will answer them. Well, if there's no other questions, I'm going to have Jeff still on. I'm going to have him see if he has any closing remarks.
Actually, David, all Davies here. I have a question for you.
Yeah.
You had a slide there with titled the late time linear trend.
Yes.
And you had a formula with K subscript S is inversely related to the slope.
Yes.
And it's, what's the subscript S? The conductivity of what?
Soil.
Soil, thank you.
Yeah, and that's the slope of that line. Actually, I'll go back there. I'll go back to that slide. I'm not sure that's just kind of a shorthand. That's not the actual full equation. It's just a relation. The slope of the line is directly related to the conductivity. There's some other information that goes into the analysis, but the reality is thermal conductivity analysis is not rocket science. It's barely anybody who knows how to run Excel and can read the ASHRAE Blue Book to figure out how to calculate thermal conductivity. So it's one of those things GLD puts in a nice clean package that's easy to use, but it's not anything that's real sophisticated. The power really the magic of GLD is the ability to get all that data collected, calculated in a short amount of time, and then be able to actually put the information to where you can see is it good data, bad data, valid test, or do we need to redo it? All right, Jeff, do you have any closing remarks?
No, David, if there's no other questions, we will post a recording if you would like to look at this again, or if you have any other questions related to the thermal conductivity testing, we'd be glad to field those at a later time. And thank you, everyone, for attending. We do appreciate it.
Thank you, everybody.
Thank you.